All right, y'all, today we are going to learn a rule. It's a great rule with a great name, and it helps make taking limits that take indeterminate form possible, and also makes them way easier. So get excited. Limits are about to become easier. This rule is called L'Hopital's rule. This is how you spell it. So go ahead and write down 4.4 notes, L'Hopital's rule. And we actually will not have to write it out each time, which is going to be great. We can write L apostrophe H, and AP graders will know exactly what you mean that you're using L'Hopital's. All right, so let's go ahead and get started. First, I want you to take a note of what indeterminate form looks like. So indeterminate form can be one of 7 things. We have 7 possibilities if a function takes indeterminate form. So we're going to write down all these possibilities. You could have 0 over 0. That's indeterminate form. You could have infinity over infinity, or plus or negative infinity over negative infinity. You could have 0. You could have infinity, or sorry, 0 times infinity. Here, I need to like separate these by commas for y'all. All right, you could have 1 to the infinity, or a number to the infinity. You could have 0 to the 0. You could have infinity minus infinity, or you could have infinity to 0. These are all versions of indeterminate form. We are going to focus on 2 versions of these. So I want you to make sure you box 2 versions. 0 over 0 and infinity over infinity. And I want you to make a note that you are going to use L'Hopital's, use LH for limits that equal these things. All right? So make a note to yourself. If you get 0 over 0 or infinity over infinity, that's when you want to use L'Hopital's rule. Okay, here we go. Here is the rule, L'Hopital's. Assume f of x and g of x are differentiable on an open interval AB containing C. Also assume that g prime does not equal 0. So we're saying, okay, actually let's keep reading. For all x in AB, except possibly at C itself. Then, if the limit as x approaches C of f of x equals 0, and the limit as x approaches C of g of x equals 0, then here's L'Hopital's rule. You need to make sure you get all of this down. You need to write this entire rule down. The limit of f of x over g of x as x approaches C equals, you are allowed to, instead of evaluating the limit normally, you're allowed to evaluate the limit of the derivatives. So like what we're gonna do is we're gonna take the derivative of the top and leave it on top, and we'll take the derivative of the bottom and leave it on bottom, and we'll take that limit, and it's going to equal the value of this limit. And an example will obviously make this more clear, but first let's get the rule down. Very important that g prime cannot equal 0, so make sure you know that. And we use this when we have a limit equaling 0 over 0 or infinity over infinity. Okay, and then you do not have to write all of this down, this proper notation, but go ahead and listen as I explain it, and then you have to know how to use it when we solve these problems. So here we go. Proper notation for solving limits with L'Hopital's. You need to explicitly show, so we're right here, explicitly show that the limit of the numerator is 0, infinity, or negative infinity. Then you need to explicitly show that the limit of the denominator is 0, infinity, or negative infinity. So here's the thing, y'all. AP graders do not let you write like, oh, the limit as x approaches C of f over g equals 0 over 0. This is fake. This is fake math. Nothing can actually equal 0 over 0. So instead, what you do is you take these separately. You say the limit as x approaches C of f equals 0, and the limit as x approaches C of g equals 0. So yes, we are getting like 0 over 0, but we're not lying to the AP graders because that makes them angry. We're not going to say it equals 0 over 0, the limit. We're just going to like show that they do that separately. They equal 0 separately, or both equal infinity separately. All right, so that's how we're going to start these problems. Then you need to say, or you don't have to say indeterminate form, but I'm going to be writing indeterminate form. You have to say L'Hopital's rule. And instead of saying L'Hopital's, we're going to write L'H. AP graders know that that means you're using L'Hopital's. You have to tell them when you're using L'Hopital's. They want to know that you know you're using that. All right. And then we can write the new limit. We can say, oh, this old limit that we were trying to solve is actually this new limit where we have the derivative with respect to x on top and the derivative with respect to x on bottom. Not to be confused with the quotient rule. This is not a quotient rule. It's just the derivative of the top over the derivative of the bottom function. Okay. Finally, you solve the limit. You solve this limit. Instead of the first one that gives us indeterminate form, you solve the limit of the derivatives. Okay, so now let's do an example of this. And we are going to use all of these steps. So like hopefully you paid attention. If you want to write them down in your notebook, you can always go back and do that. But that's what we're using when we're evaluating these. I'm showing you how to evaluate these limits to get full credit on the AP exam. So if you do it this way, you're going to be okay. If you skip steps, you might not get full credit, even if you're getting to the right answer and doing the right stuff. Okay, so here we go. Now, you may start taking the limit. You may go, oh, okay, I'm going to take this limit equals, and then you say 4 minus negative 5 square root minus 3 over, I'm substituting right now. I'm substituting, just plugging in negative 5 for x. And then we get square root of 9, square root of 9, minus 3 over 0 equals 3 minus 3 over 0 equals 0 over 0. All right, don't write this yet. You may write this on the AP exam. You may go, oh, I know how to solve this limit, and you start substituting, and then you get equals 0 over 0. This is what I'm talking about. The AP graders do not accept this because nothing can equal 0 over 0. So if you write all this out, good. I'm glad that you figured that out. You figured out that this is indeterminate form, right? But you can't represent it this way. So instead, once we recognize that, I know this is a pain, but you need to erase that and be like, oh shoot, I have 0 over 0, it's indeterminate form, I need to use L'Hopital's, but I'm not allowed to write equals 0 over 0, so here's what I have to do now. I erase all that, and I take these limits separately, the top and the bottom limit separately. I say, okay, the limit as x approaches negative 5 of 4 minus x, square root of 4 minus x minus 3 equals 0. And the limit as x approaches negative 5 of the bottom, x plus 5 equals 0. So we have to show that separately. We cannot write 0 over 0. Then we say, so we have indeterminate form. All right, now that we've done that, we know that we're ready to use L'Hopital's rule. So I'm going to represent that by doing L'H, and again, you have to tell them that you're doing L'Hopital's. And then we're going to write, okay, the limit that we started with as x approaches negative 5, and you have to do it this way, y'all. I'm not like trying to do extra. I'm trying to show you exactly what you need to do to get full credit on the AP exam. So I literally just like copied this limit, right? I say this limit is equal to, and now I'm using L'Hopital's. The limit as x approaches negative 5. And what does L'Hopital's tell me? It says that limit is equal to the limit of the derivative on the top and then the derivative on the bottom. So I need to find the derivative of this numerator and the derivative of the denominator. The numerator is going to be a little bit trickier, so let me do the denominator really quick. What's the derivative of x plus 5? 1. Okay, so there we go. Did that one. Now let's make sure we get the derivative of the numerator correct. So I'm going to come over here to do that. We have 4 minus x minus 3, the square root of 4 minus x. So that's the same as 4 minus x to the 1/2 minus 3. This is a chain rule. So we have u equals 4 minus x, v equals u to the 1/2. And then when I take the derivatives, I get -1, and then I get 1/2 u to the -1/2. So this derivative is -1 over 2, and then we have square root of u, which is 4 minus x. Okay, so I've got that derivative, and I need to put that over here on top. So I'm going to do that. We have -1 over 2, and then square root of 4 minus x. Sweet. Now, this is all over 1. Anything over 1 is just itself. So let me simplify this. This equals, remember, you cannot drop your limit. Never drop your limit. That's not allowed. So we have the limit as x approaches -5 of 2 times the square root of 4 minus x in the denominator, all under -1. Okay, now let's solve this limit. So our last step is to actually solve the limit by substitution. So now I'm going to do that. Equals, plug in -5. We have -1 over 2, 4 minus -5 in my square root, equals -1 over 2 square root of 9 equals -1/6. All right, y'all. I don't know if you think this is super cool, but I think it's super cool. We had 0 over 0. That was indeterminate form. And now we have an actual limit. It was super easy to get to that limit. All I had to do was take the limit of the derivative on top and the derivative on bottom, and I got to the actual limit for our original function, -1/6. All right, cool. So that's how L'Hopital's works. Let's do another example. Here we go, write this one down. The limit as x approaches -infinity of x squared over e to the -x. Okay, so if we evaluate these separately, we're just going to go ahead and evaluate them separately because we know that we're doing L'Hopital's today, so we're going to have to use L'Hopital's. But if we evaluate these separately, the limit as x approaches -infinity of x squared equals -infinity squared, that's going to be infinity. And then e to the e to the negative infinity, that's e to the positive infinity, that equals infinity. So if we were to evaluate this, you would have gotten infinity over infinity, which is not cool. That's not okay. That's indeterminate form. So now we need to use L'Hopital's rule. So we say this is indeterminate. And now we move on to L'Hopital's. So L''H, we have to tell the AP graders that we're using it. Then we copy down what we started with, the limit as x approaches -infinity of x squared over e to the -x equals, now I'm using L'Hopital's. I copy limit as x approaches -infinity, and then I take the derivative of the top, 2x. Put it over the derivative of the bottom. Y'all, this is like a mini chain rule. And just as a quick trick, the derivative of e to the x is e to the x. Well, the derivative of e to the -x is e to the -x, but times whatever the derivative of my inside function is. So times the derivative of -x, which is just -1. So -1 times e to the -x, that's the derivative of the bottom. We just did a quick chain rule. Cool. Now let's plug in, or let's find these limits. So equals, and we can think of it as 2 times infinity, so that would be infinity over, if we're imagining plugging in, we get infinity over, and then we have negative infinity. Yeah, okay, cool. Time out. Infinity, this would be infinity. Y'all are going to hate this, but you're going to love it at the same time. We can do L'Hopital's twice. So I just noticed that 2 times infinity, that turns into infinity. And then this is negative e to the infinity. Well, that also turns into negative infinity. So we actually have to use L'Hopital's again. So let's write this down. Limit as x approaches to negative infinity of 2x equals positive infinity. The limit as x approaches negative infinity of negative e to the negative x equals negative infinity. So we have indeterminate form again. Good news. We can use L'Hopital's as many times as we need to. So let's try to use it again. So L apostrophe H, we currently have the limit as x approaches negative infinity of 2x over negative e to the negative x. Now we're going to do another round of L'Hopital's. Let me do this one in blue. L apostrophe H. Now we're going to say, all right, let me take the derivative again of the top and the bottom. Derivative of the top is 2. Derivative of the bottom is, that's positive e to the negative x, because we multiply the negative 1 out again, and it turns positive again. Now we substitute. And you can already see that we have 2 on top, and then e to the positive infinity when we like plug in, or imagine plugging in. And e to the infinity goes to, I don't like to write equals here because like we're kind of just imagining. So we have 2 over e to the infinity. We're like thinking about what that looks like. E to the infinity goes to infinity. So this is kind of like 2 over infinity. So anything divided by infinity is going to be 0. That's our answer. Boom. Done. So sometimes you might have to use L'Hopital's twice. That's kind of the reason we did that problem. All right, we have one more problem. The table below gives values of a twice differentiable function, y equals f of x. That just means you could take the derivative twice if you want to. Use the table to find the limit. If it exists, justify your answer. All right, so we are going to start by looking at the limit of the top and the bottom. So sometimes when you have like fractions, it's just good to start by looking at the limit of the top and the bottom separately. So we have limit as x approaches negative 2 of f of 3x plus 2. And then we have the limit as x approaches negative 2 of x squared minus 4. All right, if we plug in negative 2 into this x squared minus 4, we get negative 2 squared. That's 4 minus 4. That equals 0. So we already have a problem. We're dividing by 0. Like when we solve this limit, we're dividing by 0. Or when we substitute. Let's test the other one. So if we plug in negative 2, I'm just going to like do this over here. F of 3 times negative 2 plus 2. That's the same as f of negative 6 plus 2. That's the same as f of negative 4. All right. This equals, let's find f of negative 4, 0. So we do have a case of 0 over 0. This is indeterminate form. So what are we going to use? L'Hopital's. So let's use L'Hopital's. And this one is a little weird, but we're not going to be freaked out. It's kind of like we have to take like a symbolic derivative, but we know how to do that. We're not going to worry about it. Limit as x approaches negative 2 of f of f of 3x plus 2. And y'all, I'm just copying what we started with to start. I'm not doing L'Hopital's yet. Okay, now I'm going to do L'Hopital's. That's going to turn into the limit as x approaches negative 2 of the derivatives. So derivative of the bottom is the easier one. What's the derivative of x squared minus 4? 2x. Derivative of the top is a chain rule. So let's do that derivative over here. I'm just going to like use this area as scratch area. So we have f of 3x plus 2. We need to find a derivative. The inside function u equals 3x plus 2. Then v equals f of u. So the derivative of the inside is 3. The derivative of f of u is f prime of u. And we need to plug back in for u, so we have f prime of 3x plus 2. Sweet. So now we just need to multiply these to get the derivative of the top. So derivative of the top is 3 times f prime of 3x plus 2. Sweet. Let's try plugging in to solve. Equals, let's try substituting. 3, we're now solving the limit. 3f prime of, I'm plugging in negative 2. So we have 3 negative 2 plus 2 over 2 times negative 2 equals, we have 3 f prime of 3 times negative 2. We already did this, y'all. We went through all of this over here. So I know that turns into negative 4 over negative 4 equals, all right, f prime of negative 4. F prime of negative 4 is 8. So we have 3 times 8 over negative 4. That equals 24 over negative 4, which finally simplifies to negative 6. Done. L'Hopital has helped us solve that limit. Thanks, L'Hopital. Okay, y'all. That's it for today. Get some practice done. And yeah, let's go practice.